Hello, Michael. How are you?
I'm doing well. How are you?
Good, thank you. Thank
Good.
you.
How's Colombia been?
Oh, very nice. Well, I have been in quarantine,
Right, right.
but it's nice to be home.
Yeah.
Yes, yes.
It's like Colombia is basically right on the equator, right? So it's not like it's winter down there
No,
or
no,
no,
yes,
yeah.
exactly. The equator passes through the south of Colombia, so it's
Yeah,
very very nice weather all year. I mean, it only depends on the altitude where
I
you
see.
are.
I see.
So Bogota is high in altitude, so it's not that hot. I
Right,
mean,
right.
it yeah. I have a jacket. I don't know why. It's not that cold too, so it's
Sounds
yeah,
nice.
Too much
yeah.
air conditioning.
Yes, and then we go down the mountain and it's very hot.
I see. I see. Yeah.
And I heard the cops, so you must be getting into trouble. Some cops or an ambulance or something was going by.
Now, yes, I mean, my parents live in a place where there is a lot of noise, unfortunately. So,
Hmm.
yeah, yeah, yeah,
So
yeah.
you're
It's the
quarantining
fifth
with your
floor.
parents?
I'm stay. Well, no, I mean, I'm quarantining my parents' place while, and then I'm going to go
Gotcha.
to where they are now. They are in a small house in Girardot that is in down the mountains,
Oh, okay.
and I will go there actually tomorrow morning. I will try. We will go there, and I meet them there after. Yeah, yeah, after the quarantine.
Very nice.
Yeah, yeah. Just looking forward to see them. So I think we have 19 people. So,
Yep.
but you
And
did.
it looks like we're live on YouTube now, so I think we can go
Yes.
ahead and get started. So yeah, why don't you just go ahead and get started?
Okay, great, great. Well, it's a great pleasure for me to continue the lecture that I started on Monday. So on Monday we started to discuss about the SUN symmetry in the collisions of alkaline atoms, and I briefly summarize how a clock operates. So, but my goal today is trying to tell you a little bit more about how collisions actually modify the operation of the clock on one hand, and on the other hand, how we can use the clock to measure them and start to access interesting many-body physics. So the slide that I finalized last lecture shows that, well, the advantage of SUN physics is that instead of having a SU-S scattering length that controls the collisions, actually we only have scattering parameters that are determined by the symmetry of the collisional partners. So if we have a nuclear spin degree of freedom and we have an orbital degree of freedom, and how this combine in a symmetric or antisymmetric way is what allows I mean, is what determines what type of collisions we will have. So last time I was mentioning that if we have if I have a spin a polarized gas that is nuclear spin polarized, then if we have symmetric orbital degrees of freedom, then we are going to be dominated by p wave interactions, and therefore, and the only way that I can have an S wave interactions if for spin polarized atoms is that I anti-symmetrize in the orbital degree of freedom, because that allows me to have asymmetric spatial wave functions true and that can collide via S wave. But on the other hand, if we anti-symmetrize the nuclear spins, then we start to be open to actually S-wave interactions if we have a symmetric wave orbital degree of freedom, but also I open a p-wave channel if I have antisymmetric of both. So with that, I mean, I know that it's a little bit complicated, so I want to start with the simplest case that we can all understand simpler, and that's actually how the experiment worked out. So actually, optical lattice clock don't want to have many nuclear spins. It's bad for them, as we will discuss. So instead, they want to operate with a nuclear spin polar gas. So they optically pump. They put all the atoms in the spin 9.5 or minus 9.5, as I indicated here. And what we are going to use as a effective spin degree of freedom is the ground and the excited orbital states. This is what is going to allow us to understand, to actually use the clock, and because the energy split in between these states is the one that we want to measure. So let me start with the knowledge that we have now, write the many-body Hamiltonian that rules the dynamics of atoms in the clock. So, the simplest way, of course, is to start by writing a field operator. These are fermions, as I mentioned. So, and the field operator will satisfy the characteristic fermionic anti-commutation relation. So these are field operators that create a particle. In general, we can have nuclear spin m and orbital level alpha, but in this case we are going to fix this m to a fixed number. So basically we only worry about the alpha and the beta, that means E and G. And well, these are the characteristic fermionic commutation relations. But now with that, we can write a Hamiltonian. As I said, as I show here, I removed the M because it's always 9/2, so we don't worry about the nuclear spin. And then we can have the characteristic terms that describe the many-body dynamics. Here, we have the kinetic energy, and we have the external potential, that in this case is going to be a lattice potential along one direction, as we will discuss later, but this is the generic single particle terms. And then, as I discussed before, we are in the clock, we are going to be sensitive not only to S wave, but in addition to P wave interactions. So the S wave interactions are characterized by we call EG minus term, and these are the characteristic density interactions that you write for spin 1/2 fermions. Yes, so you have the number of particles in the E and the number of particles in the G. These operators, the anti-commutation relations of the operators, guarantee that only singlets collide via S-wave interactions. And now the part that perhaps you are not that used to is the case when we have the P-wave interactions. Remember last time I introduced the pseudo potential that had KK prime, because now we are in position, the pseudo potential translate is, you see that I have this gradient here. You have the gradient dot gradient. This is the K dot K term. And you can see here that I have this term that is kind of the gradient of the first term, of alpha. Then I have the beta minus alpha and beta. This is to guarantee that, remember that P-wave interactions require antisymmetric wave function. That's the requirement because it's L equal to 1. So this way that we write the pseudo potential, these gradients that appear here is just the way that you make sure that you have the atoms are collided in the L equal to 1 channel, in the antisymmetric channel. And then, well, we have the characteristic, last time I introduced the idea of Ramsey spectroscopy, that we have the tuning of the laser respect to the atomic transition, and we have the drive, the Rabi frequency here. So it's all what we discussed last time, now written a little bit in a many body language, but the same physics. So let's try to understand term by term what this Hamiltonian is telling me. Okay, so here the densities, this is the number of atoms in the excited minus number of atoms in the ground state. All right, so this is a mess, of course. This Hamiltonian is very complicated, and the point is that we need to understand this Hamiltonian to understand what is happening in the clock. But there is a key ingredient that we have advantage of, is that, remember I told you that this is the centrifugal barrier that prevents, that suppresses collisions. So collisions, even though are important for the clock, they are weak. They are very weak. So in some degree, you expect that you can use perturbation theory. And that's going to be our key tool for that. But okay, so let's go back to our system. And remember that the optical lattice clock uses a deep lattice potential. And for them, the tunneling between lattice sites for the clock operation is almost 0. So instead of looking at all these different lattice sites, let's blow up for a given one lattice site here. And this lattice site first feels like an harmonic potential in the X and Y direction, yes, because of the confinement, it's a Gaussian profile. So what we have is a potential that along the XY direction, and we are occupying the lowest orbital along the Z direction. The lattice is so deep that I occupy the lowest Warner orbital, and on the other hand, along this direction, I can have many different vibrational levels. So because of that, a convenient basis is to go to harmonic oscillator basis. So, and I'm going to write my field operator in terms of, well, the wave function is the ground state of this along the lattice direction. And then I will have the harmonic oscillator labels, that the harmonic oscillator states that can have occupation Nx or Ny. And this field operator C is that a field operator that creates an atom in harmonic oscillator Nx, harmonic oscillator Ny along the Y direction, and the Warner orbitals along the Z direction. So this is the standard way I'm going to expand my single particle terms in that way, because the single particle physics is the dominant one. So, and of course, we are all familiar that harmonic oscillator eigenstates can be written in terms of Hermite polynomial times a Gaussian. So this is the basis that we are going to use. Now, the point is that, and this is nasty algebra, but bear with me because everything is going to be simplified. I'm going to replace this expansion of the field operator into the many-body Hamiltonian. Yeah, and when you look at that, I'm going to focus here on the interactions. That is the part that is non-trivial. The interaction, remember, you have 4 field operators. And when I plug these 4 field operators into the interactions, therefore, I'm going to have 4 of these creation and impulsion operators in harmonic oscillator basis. Yes, so I have this type of operators. I have, because the interactions, the collisions are 2 atoms collide within harmonic oscillator, for example, n prime and n3 prime and n2 prime, they collide, they're annihilated and emerge in another different harmonic oscillator level, n prime and n. That's the collisional physics, and the levels, the subscript alpha and beta are going to keep track of if it's between ground or excited state atoms. We will work this out. I mean, I'm just trying to illustrate the procedure, and we are going to then simplify it significantly. But something that I want you to pay attention is on the p-wave integrals that are going to be the ones that are key. So these coefficients that I'm going to have are going to be this type of harmonic oscillator wave functions that are going to be included these are the mode integrals. Yes, so basically if I go back to my expansion to this field operator, I'm replacing my field operators here, and then they're going to, I have the field operators, but they are going to have the mode overlap coefficients, yes? And the lobe overlap coefficient, especially, for example, for the P wave, is going to involve some gradients. So all what I want to say is that these P wave coefficients are going to have a gradient, for example, an overlap along the X direction, but a gradient along the Y direction, or a gradient along the Y direction and an overlap along the X direction and an overlap along the X direction. This is a little bit technical, but I just want to understand what is the procedure. So you are going to have these S-wave overlaps are going to be product of these 4 harmonic oscillator states, and the P-wave overlaps, are going to have these gradients that are involved from the P-wave collisions. And you can do these integrals numerically and get the value of the coefficient, but we're going to get insight in what these integrals mean. I mean, at the moment, it's just the procedure, the formal protocol. So now let's try to go into the simplifications, because other way we cannot solve the problem. The simplification here is that the interactions that June is measuring the clock are of the order of hertz. These are the strength of the many-body shifts or collisions modification. But on the other hand, if you look at the harmonic oscillator levels, they are split because his lattice is very deep and then generate an effective trapping potential. They have frequency of the order of 500 hertz. So it's really big energy difference between the interaction energy and the harmonic oscillator spacing. So you can imagine that to a good approximation, the interactions cannot make 2 atoms collide and change the energy levels, because changing the energy levels will involve generically a cost that is of the order of 500 hertz, and interactions are weak enough to prevent such type of processes. So this is going to simplify my physics enormously, because that means that my atoms are going to be fixed in these harmonic oscillator levels. They're not going to move, and you can imagine then that we will have a lattice, but in this harmonic oscillator space. My atoms are going to be pinned in these single particle orbitals. They are not going to move, and the only thing that they can do is that they can exchange their internal orbital degree of freedom if it's ground or excited. That's the only thing that can happen in this system. And as I'm going to discuss, in these harmonic oscillator levels, the interactions between the atoms can be long range, because even though the collisions are contact, as we know, the atoms have to bump into each other. In this mode space, the atoms are highly delocalized, and therefore an atom in one mode can see an atom in another mode very far apart, because these atoms are delocalized in this mode space. Yeah. So this is one of the interesting parts, and this is what I want to try to walk with you slowly. So let's
Can I
start.
ask a question?
Yes, please.
So is the quantization along the y and the x the same frequency?
They have the same frequency. Yes, I write a radial part. Yes, in principle, it's not a big deal, but yes.
But then could there be a situation where one atom just scatters like from 1 to 1?
Excellent question, and this exactly can happen. I mean, in principle, there is the trap is not completely harmonic, so the spaces are not completely symmetric. So you have an atom in N and M, then there is not completely, I mean, N plus 1 and N minus 1 is not completely satisfies energy conservation because there is a non-linear behavior of the energy levels. That's at one point. The second point interesting is that what happens is that these collisions that change our modes but lie in the same energy shell, for the observables that they measure in the experiment, it's like they have the same, they will remain in the fixed orbital, because what matters for the observables that the June measures is kind of the energy shell. So they are changing really the modes, but on the context, because they have the same energy conditions, they don't going to modify the observable that they are going to measure. So it's an approximation. It's interestingly, works remarkably well, and we have benchmarked it many set of experiments. But this gave us a headache at the beginning, these mode-changing collisions. We wrote a lot of papers trying to justify that, but it works. So, excellent question. This is and bear with me. I mean, it's an approximation there. But for example, John Thomas later, he have written a few papers where he always instead look at collisions in energy shell. That's how he calls that. So we call it we ignore these mode changing collisions, but the physics is very similar. Mm-hmm.
Thank you.
Great, excellent. So let's go. You have excited atom.
Yep.
Yes, so to clarify, you have an excited atom TRB 0 and a ground atom 1s0 in individual lattice size. Yes, that's an excellent question too. Thank you for asking. So the point is that the experiment operates in a Ramsey sequence, where initially we have a spin polarized gas. Because of Pauli exclusion principle, initially all the atoms are in the ground state. So because of Fermi statistics, at time equal to 0, you only can have one atom per mode. You cannot have two identical atoms per mode. And then after he has that, he applies the pi half poles. So he changes an atom down in mode N to a superposition of up plus down in the same mode. So up plus down in the same mode N. So it's one atom per side, but then what changes is you have a coherent superposition between the spins and between the internal levels, the orbital levels, and then this can evolve laterly because of collisions, as we will describe. I forgot. Yeah, exactly. Yes, exactly. Fermions is important for us. All right. So now if we go back and we look at the four operators that we have in our Hamiltonian, then you can see that the only conditions that I am allowed that forbid mode changes is when these two operators are the same in the same mode, and these are in the same mode. That means it's a density term. Yes, so you can see that you have four operators and two of them have to be equal. So the only thing that you can have is a term when you have this equal to this and this equal to this, and you can see because the alpha index is the same, these are going to be proportional to a sigma C term, where this S operator can be written in terms of fermionic operators like this. So for example, if you are going to have an S plus operator, you can see that an S plus operator is just you destroy, this is at mode N, you destroy a particle in down and create it in up. Yes, this is the S plus operators. And the C operator is just going to be proportional to the number of atoms in E in the mode N minus the number of atoms ground in mode n, and well, we will have to divide by 2 because of that. So this is the SC operators. So in other words, the contribution of the Hamiltonian has density in the interactions that can be written in the form of SCSC, like Anton Rydberg atoms, it was also something like SCSC, plus some type of, we call it exchange interactions that are flip-flops, that you have S plus S minus interactions between the particles. So with that trick in our hand, let's try to see what the Hamiltonian looks like. And for that, let me start by considering what happens with only 2 atoms. Start with 2 atoms and let's try to understand what is the physics. So imagine that I have 1 atom, they start in the ground state, and therefore I have 1 atom in mode N1 and another atom in mode N2. Yes? And I remember, I have a fixed particle, only 1 particle per mode, but the internal levels can be different. So what type of states I can have? I can have a singlet and I can have 3 triplets. The singlet has antisymmetric in the EG degree of freedom, but because of Fermi statistics, it has to have a wave function that is symmetric in the spatial indexes. Now there are the 3 triplet states. Well, this interaction, therefore, if I try to see how these atoms collide, because this wave function is fully symmetric in the space, spatially symmetric, it can collide via S-wave interactions, and the associated scattering length is EG minus. Now the other triplet states, can be in the ground, excited, or the triplet 0 state, ground plus excited ground, because they are all symmetric in the orbital degree of freedom. They have the antisymmetric in the spatial degree of freedom, and therefore they need to collide via p-wave interactions. So we have the first one is proportional collides via BGG cube, the second BE cube, and the third BEG cube. There are 3 different scattering volumes associated with that. And therefore, if I'm going to write the matrix that determines the collision of these particles, or even the more generic physics of these particles in this singlet and triplet basis, I'm going to have a 4x4 matrix, where on the diagonal, I have the BGG, BEE, BEG. The singlet collides via UEG. I'm missing a minus here. They have the corresponding detuning. There is +1, -1, and 0 for the triplet 0. And in addition, if I have a drive, this is only during the pulse, the triplet minus is coupled to triplet 0, and the triplet plus is going to be coupled to the triplet 0. Yes, because the laser is a single particle Hamiltonian that is of the form, for example, S plus in this basis, so it flips ground to excited or excited to ground. That's what it does. So, question: is the triplet, if for example, can I couple the singlet? Is it possible to have a matrix element between GG and GE minus EG, the singlet state? Is it possible?
No.
Why?
Because it's kind of the same way you think of the van der Waals interaction versus the dipole exchange interaction. Yes, when you split both of these, into submatrices, you end up with 2 different bases that describe, one that describes the dress state and one that describes the start shift state. Yes, GG describes the start shift, and this would describe one of the dress states. That's not a very good answer.
Well, the question is actually tricky, and I can tell you that it gave us a headache for almost 2 years. And the reason is that in principle it can. Yes, I can teach you why. This atom G lives, I'm writing them there. This G lives in the harmonic oscillator label N1, and this other atom G lives in the harmonic oscillator N2. Yes, they have labels. They are in a given lattice site. Now, what happens is that the drive, the Hamiltonian that is driving the atoms is a plane wave, e to the AKX, yes? And the matrix element is going to be the matrix element, for example, that couples, this is the matrix element that fills this G atom, and then there is another matrix element that fills this other atom. Yes, so let me call this is proportional to omega 1. I mean, I'm going to put omega 0 times omega, and this is omega 2. So in principle, the Rabi frequency that they are filling is not exactly the same. It's not exactly the same necessarily. Yes. So so let me put here, this is K dot here. I'm putting a K dot here, K dot. So the point is that if the laser is aligned along the C direction, this matrix element K dot X can be 0. But there is a tiny misalignment, so there is a component of the wave vector along the X and Y direction. Then this matrix element here has a AKX, and therefore the matrix element omega 1 and omega 2 is not the same. Yes. So if it were the same, if omega 1 is omega 2, that is the case that I'm considering here, omega 1 is equal to omega 2, there is no way, because imagine if I'm going to write what happens, G1 goes like G cos theta plus E sin theta, or theta half. Yes. Remember, theta is omega times T. Yes, so E sin theta half. And I'm going to multiply the second atom by the same thing. And therefore, when you multiply the two, you have only a symmetric state. You have a superposition of GG plus EE plus EG plus GE. So you go from triplet to triplet manifold. You cannot leak out of from the triplet to the singlet. However, the physics is very different. If I am going to have something like, we imagine that we have the atom in GG, but then this rotates, the first atom rotates like G cos theta 1 divided by 2 plus E sin theta 1, and the second atom has a different rotation. This is cosine theta 1 tilde plus E sin theta 1 tilde, or theta 2, maybe it's better to call it theta 2. So now I have different components of EG, and then I will have a superposition between singlet and triplets. Yeah. So this is one important part so for the case where when the case where only have E and G are the same. So in this case where omega 1 is equal to omega 2, then I only couple between the triplets to triplets. But if there is an inhomogeneity, I can couple to the singlet. So there have been a lot of questions in the chat that I have not answered. Sorry for that. So basic question, but what happened to the other 4 scattering parameters we had last time? Okay, remember, we are only looking at nuclear spin polarized states. Yes. So if we go back to my table, we can go back to the table. Let me do that. Then we go back to my table.
Oh, I was just going to say that Caden answered my question. So.
Okay.
All is well. Yeah.
Okay. Great. Okay. Perfect. Any other questions then, or can I seems that people are on board? Okay. Great. Okay. Yes, for this spin polarized case, when for the spin polarized case, when I have, this is the only matrix element that I have. This is the BGG, BE, BG, UEG, and then it's only coupling between the triplet states. Now, well, as I said, if omega 1 is different to omega 2, I can open a coupling to the singlet channel. And the important part is that the singlet does feel an S-wave interaction that is much more larger than the P wave. So at the beginning, when Jung was measuring these density shifts, we thought, oh, his clock is misaligned. The wave vector is not completely aligned to the lattice, and that's why they are seeing density shifts. It ended up being not the case, as he can align everything perfectly well, and the misalignment is really tiny. So it was not the explanation of the density shifts, as we will show. But in principle, you have to this is something that generated at least 3 theoretical works trying to explain the density shifts in terms of this misalignment problem. It was not the case. So let's go back then, and now we know that is not the case, and just restrict ourselves to let's go to write the actual interaction Hamiltonian. Imagine that the drive is completely homogeneous. We don't care about any issues with the drive, and let's try to understand the interactions. This spin model looks awful, but this is another way to rewrite the simple matrix. I have BGG, BEE, BEG, and UEG. Yes, this is in the basis that I had before. This simple diagonal matrix that have this interaction can be written in terms of spin operators in this way. So let's try to understand a little bit more. So here, all the assuming is that now this is 2 atoms, but of course the collisions are pairwise, so I can sum over pair of atoms. So that's why I'm assuming pairs of atoms that are I different from J prime. So this is but you can just focus and put J equal to 1 and J prime equal to 2. So when you look at this Hamiltonian, we have a term that is S dot S, that is SU2 symmetric. We have a term that is SCSC, that is an icing Hamiltonian. And then we have what we call interaction. These are going to be very important for the density shifts that they measure, as I'm going to be explained. But if you look at this Hamiltonian, we can do the exercise, for example, that to show that this Hamiltonian is going to give me these very trivial matrix elements. For example, imagine that I'm preparing the atoms in the ground that have an interaction that is BGG. Yes. So if I have an interaction BGG, this S dot S just give me 1/4. Yes. So this is 1/4. If I have SCSC, give me 1/4. If I have SC, I have just in this case I have -1/2, and minus 1/2 for the other atom, and this is just the identity. And then if you can work out yourself, if you sum J perp plus this minus this plus this divided by 4, if you sum, for example, you start to see that, for example, these matrix elements here is going to cancel out the matrix element that you have from here to this term, and you are going to see that, you can see that by when you rewrite these matrix elements, you are going to find that you have this very trivial form. If you can do the exercise, that would be great, that you show that this matrix element has exactly the form of this Hamiltonian. Okay, but there is going to be one very, very, very important case. Now, if I'm starting with my atoms all in the ground state, now if I am the frequencies, the Rabi frequency that each atom experiences is exactly the same. I'm starting with a state that lives in a system that is fully symmetric. The total S is equal to B total n half, yes? Because it's in a fully symmetric manifold, all the atoms are ferromagnetic, they are doing the same, so the total S of my system is n half. So then what happens is that if everything is going to be kind of collective, this term preserves the total S, and it's going to be a term that is not going to be that relevant. And the most important physics is going to come from these other terms. I'm going to explain that in more detail a little bit, but just be aware that at some point, these 2 terms are the ones that are going to determine the collisional physics that I want to see in the clock. Any questions so far? I know that is a lot of notation and a lot of math, but just wanted to make sure that you are following me.
Oh, when you were talking about the collision terms, I guess you mentioned there was one term which was like density, and there was one where n and n prime exchange themselves.
Yes.
Can there be another term where you have some n plus n prime coming in and turning it into n double prime and n triple prime, where n plus n prime is same as n double
so
prime?
you are saying the mode changing collisions when I have something that is n1 and n2 and I go to something that is N3 and N4?
Yeah, and the sum N1 plus N2 is equal to N3 plus N4.
Yes. So there, I mean, yes, that's an excellent question. That's what I think Francisco was asking. In general, if these terms conserve energy, so if the energy of these processes is the same, in principle, they are allowed, in principle. But the point is that even though it's not completely included in the model, because there are on shell, to an excellent approximation, is like these processes were not participating in the dynamics. So yes, there are these processes, they are suppressed in some sense because they actually in the trap, the energies are not linear with N. The trapping potential is Gaussian. So when you have two terms N1 and N2 and the particles collide, the energy is going to be more N1 plus some coefficient proportional to N1 squared, N2 another term that is proportional to N2 squared. So this conservation of energy doesn't happen that easy because of the Gaussian curvature of the Gaussian behavior of the trap. When they happen, I mean, if there is the rare case when these terms are happening, somehow neglecting them it's not that bad approximation. I mean, because even though they do change, if they keep the same energy for what they can measure in the experiment, is not a big difference. I know that this is a little bit hand waving, but as you will see, actually, it's an excellent approximation to neglect the terms that can change orbitals but conserve energy. I mean, they don't generate such a big difference in the model.
Thank you.
Does that answer your question?
Yeah.
Okay.
Can I ask a clarification?
Yes.
With respect to ignoring this Heisenberg term, if I look at the other terms of the Hamilton, they're also SZ. So it seems like just total SZ is conserved throughout.
Yes.
So why am I allowed to disregard this Heisenberg term?
Give me 1 second and I will answer you. Let me keep the question there. I'm going to explain a little bit in 1 second.
Perfect.
Okay.
Thank you.
So there is let me try to understand first what is the character of the matrix elements that we are dealing with. So we have these terms that I'm writing there that are chi, that are c. All of these depend on the scattering lengths that I'm talking about here. B, G, V, G, B. These are the scattering volumes or scattering lengths. But as I said before, they have a matrix overlap that depends if they're S wave or P waves. The dominant terms, because there is the Rabi frequency is not coupling to the singleted state, is going to be the triplet states or everything that is triplet. And in this case, we are going to be interested in oh Jesus, my connection is getting unstable. Can you hear me well? Okay, great. So the matrix elements that we have is the P wave interaction energies that, as I wrote before, they can be quite messy. They involve the gradients, remember, of the wave function of this. But I'm going to give you a very, very, very rough argument of why these matrix elements in many degrees of freedom, they are kind of behaving very collective. So remember that the P wave pseudopotential is something that depends on the scattering volume, B cube, and depends on the kinetic energy, K squared. Yes. So the overall behavior of this term is B cube multiply. I mean, let's match the units. This has to have n units of energy. So this is B cube, the volume of the system, and then we have the kinetic energy. I mean, because it's proportional to K squared because of the gradient. Now, if we go to imagine that instead of having a trap, I can have of a box or something like, I trying to compute what is the volume of my wave function at final temperature. So the volume of my wave function at final temperature, I have the harmonic oscillator length along the Z direction, and along the XY direction, I have a thermal cloud. The system is about microkelvin temperature. So the area along the X and Y direction, if you have a thermal fermionic gas, you can show that the extent, the wave function, the the extent of the gas along the radial direction is proportional to the temperature divided by h bar omega, divided by, of course, this has to have units this has to have units of area, so the harmonic oscillator square along the radial direction. Yes, I mean, this is just a very hand-waving argument. If you have a fermionic gas, or even a classical gas at finite temperature, the size of your system scales proportional to a square root of T. This is a Gaussian cloud, a Gaussian gas. So when you put this area, the area of the gas here, you find that you can see the area is proportional to the temperature. And at the same time, the kinetic energy of the gas is also linear to the temperature. So to a very good approximation, this temperature disappears. And the matrix element of these P-wave interactions are temperature independent. So in very extent, and this is just this very hand-waving argument, but now if you take your matrix elements and try to by hand compute what is the dependence of this wave function overlap as a function of the temperature of the gas, you find remarkable that is completely flat, is independent of the temperature. These parameters are almost, not only that, but also the standard deviation is independent of the temperature. So it's quite uniform. That is remarkable. That's very nice for the P-wave interactions. And now if you try to make an histogram of the different parameters, when you have a gas, a thermal gas, and try to look at the population of the different modes and try to by hand compute the histogram of these wave function coefficients, you find that is very sharply peak at the mean value. So the mean value is much larger than the standard deviation. So interestingly, to an excellent approximation, we are going to replace the sum of different wave function coefficients. We are going to replace it by the mean value. So instead of having to deal with these interaction parameters that we have chi n prime, n j prime, we are going to replace this term by just the mean. So instead of having this, I'm going to have a Hamiltonian that instead of having these coefficients, I'm going to replace these coefficients by the mean value, that is the sum, the thermal average of this coefficient. And then instead of having something that is SC and I and C and J, I'm going to replace it by SC squared. And this I'm going to replace it by N times SC. Yes. So now let's go back to Francisco's questions. I will have a Hamiltonian that, because of the coupling constant, I also am going to have a term that is the form S dot S. Yes. So this Hamiltonian, nevertheless, if these Hamiltonians commute with SC, commute with SX, I mean, is SU2 symmetric. So if I start with a system that at time equal to 0 is SU2 symmetric because I have all the particles in the ground state, and during the dynamics, anything breaks the SU2 symmetry, the term S dot S is just a constant and is proportional to n half plus 1. Yes, it's a completely constant term that is not going to modify the dynamics. So in this Hamiltonian, I can just really set this term to a constant, ignore them, and the dynamics of my system is going to be just dictated by this collective spin model from the collisions. I mean, it's a very...
Can you go to the prior slide?
Yes.
So this whole argument kind of hinged on the, if you really want to make it quantitative and everything, hinged on the standard deviation being smaller than the mean. Am I supposed to see that from that histogram? Because that doesn't look all that narrowly peaked to me.
Yeah, but it's the standard deviation. I mean, maybe you can see it here. The mean is about 0.3 and the standard deviation is of the order of 1/3. It's smaller than this. It's very hand-waving. I mean, I know that is... I mean, when you do the numerics exactly, you find that, I mean, this approximation worked remarkably well. In the sense, I mean, maybe the other way that we can see that is that this term here, S dot S, actually generates what we call a gap protection So it prevents the leakage of the system outside the fully symmetric manifold. So even though the coupling constants are not completely perfect, the parts that are going outside this decay manifold are going to be suppressed by this term. So that's why in some sense we have this approximation of having the Hamiltonian just as this collective spin model is a remarkable good approximation.
Actually, can you go back to, good, so I believe, can you go back to the histogram again?
Yes.
So it looks like there are no matrix elements below about 0.2. Why is that?
Well, I think the P-wave interactions, yes, so let's see, why is that we don't have this, we are talking, I mean, all this is a finite temperature. Yes, there is a finite temperature system, and in some degree, this is the fact that these interaction parameters are going to be centered around a mean, and the variant. I don't know. The variance is maybe I quoted the terms that have very weak. I mean, maybe it's also an approximation of what is the terms that have a small weight on this, but the majority of the terms are concentrated along this mean value of the
but I mean, it's very asymmetric, right? There's a long tail to larger values, but not to the smaller values. That's kind of what was surprising.
Yes. Okay. Yes, that's an excellent question. I mean, it's a consequences of these matrix elements of their mid polynomials. Basically, we are computing the histogram of these coupling constants are going to be these integrals. Why we don't have something smaller than that? Maybe when we write the 0. I mean, the smaller Hamiltonian that we have is the ground state. That's maybe this gives you a cutoff. I don't know by hand. I mean, let me think about why there is no small.
Yeah, I guess that these have some funny structure that they actually grow within, don't they? Like
yes, these interactions. That's very funny because these interactions, in principle, are P-wave interactions. So scale with the kinetic energy. So the larger the kinetic energy of my system, the larger the integral. So that's why we have this tail here. So this is this behavior actually when you plot these scales like a square root of n1 plus n2. Interestingly, this is the way that these tails scale. These small integrals, I mean, they are a little bit suppressed maybe because of, I mean, when you have, I mean, at some point we have the worst case. The small, okay, I know the answer. The smaller energy that you can have is when you have all the atoms that are in the same harmonic, I mean, like a Fermi degenerate gas, and there is a small Fermi pressure that you can get from this gas. So you cannot have a kinetic energy smaller than the Fermi pressure. So maybe that's associated with that.
Yeah, thanks.
Great. Okay, so the point is that after all this, we have been able to reduce this complicated many-body Hamiltonian to something that is very treatable. So we are going to remember from this very complicated many-body Hamiltonian that we have. Could you explain why we neglect the J and K terms? Okay, yes. The K terms is proportional to the identity. So in principle, identity is just the 0 point energy, so we don't care about the dynamics at all. Now, for the S dot S term, so I can add here a term that is J S dot S. Now, if you can see, this Hamiltonian, all these terms in the Hamiltonian commute with this S dot S. So if we start in a state that, for example, is with a well-defined S, so S equal to n½ because we start with the dynamics with all the atoms in the ground state. Then this term becomes just a constant again. It's a constant of motion that remains the same during the whole dynamics. And that's why we can neglect it. Does it make sense? Okay, great. So now we are back to a very simple Hamiltonian that is SC squared and SC. And these terms, the important part, are coming from interactions. So these are the ones that are going to be responsible for the density shifts that June is measuring. By mean is that the ticking of the clocks, the energy splitting between the ground and excited state are going to depend on the number of atoms. And let's see that. For that, The simplest theory that we can make is a mean field theory, where I have this Hamiltonian, and to an excellent approximation, instead of replacing this operator as quadratic operator, I replace these operators at 2 times expectation value of SC times SC. That means the other atoms in the gas generate a mean magnetic field that is experienced by these atoms. I'm going to see what these atoms is interacting with the rest. So instead of looking at this at the full many body level, I have my atom and I see that this atom is interacting with all other atoms in the gas. Yes, so I replace this SC by the expectation value of SC times SC. So this acts as an effective magnetic field. Yes, and then of course I have this other term. So if you, from this Hamiltonian, you can clearly see that the density, if I only have, without interactions, I have a Hamiltonian that was minus delta SC, and delta was the parameter next to XC. In the presence of collisions, this is the tuning, that is what the clock measured in a Ramsey frequency, that is the precession rate of the atoms during the dark time, is replaced by a term that is proportional to, it has an additional contributions from these other terms, that is 2 chi bar expectation value of SC by these C bar terms times n, the number of particles. So you can see that then the ticking of the clock that Jung was measuring actually is going to be modified by how many this term SC is associated with the pulse area at the beginning. So the SC is related to, actually is going to be proportional to cos theta. Yes. So for example, if theta is equal to, is minus n half cos theta. If theta is equal to 0, I have SC equal to minus n half. If theta is equal to pi half, I have my atoms pointing along the equator. So there is a
Maria,
question.
there's a no.
Let me look at this. Is mean field necessary when this Hamiltonian is diagonalized? Since no, it's not necessary, but it just gives me intuition. And if you do the exact theory, then you will have very similar physics. So it's just to make, you can exactly diagonalize and do everything analytically. That's a good question, but it's just that it gives me the intuition of what is happening, because we want to try to get a little bit of analytic understanding of what they are seeing in the clock. Yeah.
Also, for large n, I guess you can. It's systematically correct. You can do an expansion around mean field that's exact as n becomes infinite.
Exactly. We will see that there are actually in the experiment there are seen beyond mean field corrections, and I'm going to tell you about that. But for the density shift itself, as Kaiden says, for large n, in the density shift is really very, very, very mean field like. So okay. So let's do with this approximation. I'm telling you here that the density shift that they're seeing is something that is linearly with the excitation fraction, because it depends on cos theta. And this is exactly what the experiment sees. So if you see the dots are the experimental points, this is the shift, the change in the ticking of the clock, the change in precision frequency. So this change of the tuning as a function of the excitation fraction that they control by the first pulse area. This is 1 minus cos theta. And you can see that they see this beautiful linear dependence that this very simple mean field theory gives me. Yes. And why is that interesting? Because, well, first, we are able to understand what the experiment is seeing. But second, it allows to determine the P-wave parameters, because we don't know them, and actually compute them for strontium 87 is a mess. So even Paul Julien, he cannot compute these parameters. Paul Julien is the expert. You ask Paul to compute scattering lengths and he's the master. But for strontium 87 with a nuclear spin of 9.5, even he cannot compute these scattering lengths. So the beauty is that not only we were able to reproduce the experimental observation, but moreover, we are able to operate the experiment here, where the density shift was not longer an issue. And this is what allowed Jung to have the precision and the sensitivity reaching 10 to the minus 18 at that time. So now it's even, we will have to control the density shift even better, but at least operating at this magic point, we were able to control and avoid collisions during the dynamics. All right. So as I said during the Ramsey interrogation, what we are measuring is the collective value of S minus operator that has a magnitude that I explained last lecture, that was the contrast, and the phase. And the phase is the modification of the phase due to collisions. This is what gives me the density shift. Let's look a little bit more at the contrast. What happens with the contrast? That is the amplitude of the Rayleigh fringes that they measure in the experiment. Well, at the mean field level, if you have a fixed number of atoms, at the mean field level, the contrast cannot change. Or at the mean field level, what happens, the effect of the interaction is to introduce a magnetic field. The magnetic field is not going to change the length of your block vector. You are just going to precess at a given rate, but the length of your block vector is going to be the same. However, in the experiment, they have not a single pancake. They have a bunch of pancakes because it's many lattice sites. And the point is that in the experiment, each lattice site is populated by a different number of atoms per pancake. And you can see that depending on the number of atoms, each pancake is going to experience a different density shift. They're going to precess a different rate. Remember, the density shift was proportional to n, the number of particles. So what happens is that because each atom the atoms in different pancakes are precessing at different rates, then because of that, you are going to have some defacing, and then the defacing is going to modify and let the contrast decay. So atoms precessing at a different rate are going to precess and then they decay. And in fact, that's what they kind of see in the experiment. So the solid lines are the experimental points. This is the contrast of the Rayleigh fringe versus time. And you can see that this is, for example, for different tipping angles. Remember, the density shift was depending of the number of atoms in the excited state. And you can see that these are measurements done at the tipping angles that are indicated with the corresponding color, a small tipping angle, larger by half, until you go at the 0 point crossing here. And then you can see that for the small tipping angles, the mean field theory, that is these solid lines that I'm writing here, reproduce very well the experiment. Everything decays, and this decays because of the defacing of the different pancakes. But surprisingly, when you go to this phase here, this point here, where there is no defacing because there is no density shift, the atoms are just not precessing, you see that the mean field theory predicts something like that. I'm lying here a little bit. There is some losses from p-wave interactions from the excited state, but this is a detail. Still, the experiment is seeing a much faster decay. That's what you can see in the mean field theory. So what is going on here? Well, let's go back to our model that is the SC, there is failing mean field theory, and then let's try to see what happens if I have a Hamiltonian that is SC squared. So the mean field is predicting that I have something that is chi SC times SC with a factor of 2. This is the mean field prediction. And therefore, if, for example, if I have something that is expectation value of SC is equal to 0, for example, at the equator, then the mean field predicts no dynamics at all. But on the other hand, that's not necessarily the full story because we have quantum fluctuations. So basically, if you have, even if we start along the x direction, pointing, for example, along the equator, so when the expectation value of SC is equal to 0, we know that as we predict at the variance or the expectation value of SY squared, this is not 0, it's actually proportional to n divided by 4. This is just the intrinsic quantum noise of a system. You have a distribution. I mean, it's because SY, SC, and SX, they don't commute. Expectation value of this is also equal to of SC is equal to n quarter. So the problem is that I have to account for this noise distribution in order to solve for the dynamics. And the simplest way to do that is what we call truncated Wigner approximation, TWA. And the basic idea is that you imagine that you are solving the dynamics with mean field conditions, initial conditions, mean field dynamics, but you supplement for initial conditions that account for these noise values. Yes. So you solve for the mean field dynamics. In the mean field dynamics, if you have a vector pointing along the x direction, you are going to say Sx is equal to 0, as we were saying here, Sx is equal, Sx equal to n half, and y equal to 0, and Sc is equal to 0. This is what happens if we have a vector pointing along the x direction. And that's what you solve. No, what we do is that we assume that this is a Gaussian variable, Sy, that contains values, a Gaussian distribution with a standard deviation that is proportional to a square root of n divided by 4. And similar for Sc, we imagine that it's a Gaussian variable with a standard deviation that is n divided by 4. And we sample over these initial conditions and solve for the dynamics and to account the initial quantum noise of the system. And when we do that, let me just delete all of this. You can see that we magically reproduce the experimental behavior. So all these quantum fluctuations that we have at time t equal to 0 were the responsible for actually the extra decay of the contrast, and we were able to reproduce this experimental observation. So with that,
yeah, can I ask a question?
Mm-hmm. Yes.
Like, so this seems very similar to like the spin squeezing that we saw in a couple of lectures.
Yes.
So
yes.
is it possible to turn this defect into a feature? And
Perfect. Yeah, we look for spin squeezing, and I mean I was not going to cover it because at the end it didn't work for us, because besides these elastic processes, there were some extra losses that are adding additional noise in the system. So we were not able to detect this in the expectation value of the contrast that are single particle observables. But you are completely right. I mean, in principle, in the absence of this noise, if we were able to extract and measure the expectation value, for example, for Sy squared, Sc squared that are associated with the squeezing, in principle, if they were not losses, we would have seen it. We look for it very carefully, and unfortunately, it doesn't work. But June has a new experiment, and I mean, he told us 5 seconds where he's seen coherence time of 46 seconds. And now we are trying to see a squeezing in his experiment because he doesn't have very strong losses there. So hopefully in a few months, we are going to report an spin squeeze clock. Let's see, with the same mechanisms that I'm explaining here, but in a regime where losses are not detrimental. Hopefully, let's see.
Thank you.
Great. Excellent. So I told you so far the physics of an spin polarized gas. And I told you how from this very complicated many-body Hamiltonian that nevertheless is very simple, but because we only have 4 scattering volumes to worry about, we were able to reproduce the experimental observation and lead the clock to better performance. And at the same time, we gain understanding the many-body physics. Now let me jump a little bit to the other chapter and try to start to add the nuclear spin degree of freedom, because so far we have operated only in a nuclear spin polarized regime. So let me try to review some of the experimental work that has been tried to actually explore this orbital spin interaction. We call orbital SUN magnetism. So let's try to cover a little bit of that. All right. So I'm apologize because of course the Hamiltonian is going to be much messier than before, but bear with me. I mean, we are going to simplify it soon. So now we are going to have 10, for example, nuclear levels, and we're going to rewrite the Hamiltonian, the many-body Hamiltonian that we wrote for an spin polarized gas. So now we are going to have again, I mean, for the S-wave interactions, I'm going to have 4 terms, AGG, AEE, AG minus, AG plus, yes? And I'm going to have the similar Hamiltonian for the many-body. So now for the GG interactions, I can have S-wave interactions if I have atoms in 2 different nuclear spin states, yes? So if I have MM prime, that's the type of interaction between 2 spin states. I can have EE interactions also between atoms between different nuclear spin states. And now we are going to have 2 additional processes that we call the direct and exchange interactions. The direct interactions are proportional to the sum of these two terms, Eg plus and Eg minus. And these you can see that are density-density interaction terms. So if I put my Hamilton here, there is going to be a term that is proportional to the number of atoms in the ground state with a nuclear spin m, and this is going to be the number of atoms in the excited state with nuclear spin m prime. And I'm going to have also a term that is Eg, this is the direct term, and like in helium, we are going to have a term that is going to be what we call the exchange term. And this exchange term, what it's going to make is going to introduce flip-flops between internal levels. So for example, if I have two levels, the 9½ and the 7½ that, for example, I refer to this as spin up and down, and I have my states like ground and excited. If I put two particles, one in the particle in the excited state in a spin up, and one particle in the ground state with a spin down, these are going to start, because of this term, these particles are going to start flip-flopping. And this is the physics that I'm going to explain now. And this was the first target of experiments, trying to see exchange processes between Eg orbitals and two different nuclear spin states. So let's try to understand that. But a disclaimer, this is the interaction for the S-wave part. We in principle have the same type of interactions for the P-wave part, but instead of having now we are going to need to introduce the gradients, because these are going to control that the interactions need to be antisymmetric. So we're going to add the gradients to the P-wave Hamiltonian, and it becomes a little bit more complicated. Unfortunately, that's all the stuff that we need to understand when we are going to try to model the clock with different nuclear spin states. But let's start simple. And let's start with the first experiments. These experiments were done in two places, one in Lens and the other by in Emmanuel Bloch's group at Munich. So what they did is that, let's start simple. Let's start with two atoms in a single lattice site. So of course they have many lattice sites, but imagine that they prepare a system where they have atoms in an optical lattice, and they prepare atoms in the lowest vibrational level. So we are going to have atoms in the lowest possible harmonic oscillator state in a given lattice site. So we are going to have an orbital degree of freedom, a spatial degrees of freedom that is fully symmetric, and therefore the interactions that we are going to have are only going to be S-wave interaction. So let's now try to understand what are the possible eigenstates that we are going to have if we prepare one atom in the excited state and one atom in the ground state. Imagine that we have one atom in the excited state, one atom in the ground state, one atom in one nuclear spin state 5½ and the other atom in the nuclear spin state 3/2. So we already described the possible eigenstates of the system. These are just described by symmetries of the SUN interactions. I have fermions, so I have to have a wave function that is totally antisymmetric. So I have only two possible states, the plus and the minus. The plus have symmetric orbital and antisymmetric spin, and the minus has antisymmetric orbital and symmetric spin. Yes, these are the only two possible states, and these have interaction energy that is Eg plus and Eg minus. This is very simple. Now, I told you before that unfortunately or fortunately, the reason why the clock transition exists in alkaline atoms is because of the hyperfine structure. And what happens also is that these hyperfine structures makes that the ground and the excited manifold have different G factors. So in the presence of a magnetic field, what happens is that the energy levels of the excited state, the 3p0 state, this is the 3p0 state, is going to have different Zeeman shifts than the ground state. And this means that there is going to be an energy term. If you have only two nuclear spin states, there are going to be an energy term that is delta V, that is different between the ground and the excited state. This delta V facilitates eigenstates that instead are spin polarized. So in these levels, if delta B is very large, I prefer to be like this, or I prefer to be like this. Why? Why is that? Because look at the flip-flop processes. I mean, imagine that I have this, let me exaggerate it and make this delta B huge. If I start with particles here, one particle here, the flip-flop terms want me to actually flip-flop. This goes down and this goes up. So this goes here and this goes here. But you can clearly see that the energy of these states is very different to the energy of these states because of this large delta B. So delta B is going to try to instead have a spin-aligned state and not superposition of singlet and triplets. So the matrix actually, let me write the matrix that describes this Hamiltonian. You have the UEG, UEG, and then the delta B is going to couple singlet and triplet. This is a very simple two-level system Hamiltonian that they wanted to measure in the experiment. So basically in the experiment, they start by preparing an atom in this configuration. They start by preparing an atom in the excited state down and the other atom in the ground state up, this configuration. They started by preparing this configuration that is a superposition of the plus and the minus state. And they let the system evolve as a function of time. They turn off the magnetic field as much as they could, and they measure the population of atoms in the G up state. And this is just a two-level system that is going to introduce Rabi flopping. So the probability of this state is going to oscillate at a rate proportional to the energy difference between the UEG plus and the UEG minus. It's going to be asked for just sinusoidal oscillations at this rate. And actually, this is exactly what they saw in the experiment. In the experiment, they saw this very nice Rabi flopping at an energy splitting that allows them to determine this exchange value that is the difference between UEG plus and UEG minus. That's the Rabi flopping. Actually, you can see they saw in principle, very long Rabi flopping. But on the other hand, there was a big surprise in the experiment. In the experiments, the amplitude of the oscillations were really tiny. And the reason is that they found that actually there was a very big mismatch between the scattering lengths between EG minus and EG plus. Whereas the EG minus scattering length was just normal, like of the order of 220 atomic units, they found that the scattering length for the EG plus was more than 3000 Bohr, huge. So the reason why with this very large energy mismatch, in order to prepare a state that was up-down, that is what they wanted initially, require a huge magnetic field that they didn't have. Well, it was very hard to actually prepare the initial state. So that's why the amplitude of the oscillations were really tiny. So you heard from Mera Parish that this was laterly understood as what is called orbital Feshbach resonance. Basically, they understood the EG plus and this channel, the plus channel and the minus channel as two different closed and open channels that they were coupled in the short range part of the potential that behave very similar to the open and closed channel when you have two molecular states and when you actually have a Feshbach resonance. So they call this resonance orbital Feshbach resonance. And well, still, there are a lot of things to understand about this orbital Feshbach resonance, but on the other hand, they give tunability of the scattering lengths by changing the magnetic field. So this is this value. They found a specific magnetic field. They can be tuned at a different magnetic field that allows actually possibilities to explore a little bit more explore different type of physics in these systems. All right, so these were first instances of experiments.
Sorry, I think I'm missing the connection. Can you remind us like how the scattering elements like enter into this two by two Hamilton? Is
Okay.
UEG?
UEG and UEG minus are proportional to the scattering length. Yes, they are directly proportional. So the oscillation frequency that they see is proportional to the difference between EG plus minus EG minus. Yes, this is the oscillation frequency that they see. And then this oscillation frequency actually is very large.
Okay.
So because I mean, they were expecting something much smaller. The problem, I mean, what was the complication is that the experiment wanted to start. I mean, maybe to give you more details, the way that they prepared this initial state, or they wanted to prepare this initial state, is because they start 2 atoms in the ground state. 2 atoms, this is the one that they can easily prepare. They start with 2 atoms in the one state, one with nuclear spin 5½ and the other with nuclear spin 3½ And what they do is that they wanted to drive this state, GG, with a singlet configuration in the spin. They wanted to drive it or adiabatically convert it. I mean, they tried different tricks into something that was E down, G up, spectroscopically. Yeah. But in order to drive this state is an eigenstate of the system in a huge in a magnetic field that is much larger than the energy difference between these two. So that was the complication, because the UEG and UEG plus, they were so different that in order to prepare this state, they needed to apply a huge magnetic field that was not easy in the experiment. So that's one of the first complications that they started to see, because it was not expected to have such a big mismatch in scattering lengths. In strontium, it's not like that. This is in ytterbium, actually. So that was one of the complications. At some point, they realized, oh yes, there is new physics that is coming, that is emerging, and this is arising because of this Feshbach resonance, orbital Feshbach resonance that is happening, that leads to this very complicated mismatch and in additional zone losses in the system.
So I should think that the small contrast is because the fidelity of the state prep is actually small because of this difficulty. Okay.
Yes,
perfect.
it was difficult to prepare the initial state. It just was a little bit of, I mean, it was mostly a triplet state with a little bit, I mean, it was not this state that they prepared. It was mostly a minus state with a tiny admixture of the plus. And that's why the contrast is so small.
Perfect. Thank you.
Great. The SUN orbital magnetism now in the optical lattice clock. I mean, what we saw before was only 2 atoms. Now we are trying to go to the zoo of having many atoms. Oh, my connection is unstable. Hopefully you are hearing what I said.
Yeah, you went out for about 5 seconds, but I think it was when you were just transitioning, so I think it's okay.
Okay, great. Excellent. So we are going to put flavors, color in our clock, and we are going to not only populate a single nuclear spin state, but we are going to have other atoms in the other nuclear spin state as an spectators in my system. And I want to use my clock to measure density shifts and tell me some information about these SUN interatoms are going to interact with the rest of them. So the idea is that, well,
Maria, you broke up again.
We are
You
going
might
to
just
interrogate.
wanna
My laser is
repeat.
going to. Okay, I'm sorry. So the laser is going to interrogate the 9½ transition. So I'm going to prepare all my atoms I'm going to have initially a mixture of the different nuclear spin states, but my laser is only going to be resonant to the 9½ transition. So I'm only going to transfer to the excited state atoms in the 9½ nuclear spin, and these other atoms in other nuclear levels, I'm going to use them as spectator atoms. So what is the beauty of the SUN symmetry? The SUN symmetry tells me no matter how I distribute my atoms in this in the different nuclear spin states, as long as I fix the population, then no matter how they are going to be distributed, I'm going to measure my Zen density shift, because I'm going to measure the density shift between these and interacting with these other spectator atoms. So it doesn't matter how they are distributed, as long as I have the same number of atoms as spectator atoms, I should measure exactly the same density shift. So the density shift that the clock is going to measure is coming from the density shift between the nuclear spin polarized atoms that we understood and we computed, that is this formula that is linear with the excitation fraction, plus the shift that these atoms is interacting with the others. But this density shift, because of the SUN symmetry, is only going to be proportional to the number of spectator atoms. That's it. Everything is going to drop out of the problem. And well, proportional so to some scattering parameters that are going to be a combination of S wave and P wave. So that's exactly what they saw. So they are going to measure the density shift that they measure as a function of the excitation fraction. And remember, before we saw this linear slope for nuclear spin polarized atoms. So if I have a sample that is fully nuclear spin polarized, that's what they measure. This is the slope that measured, that is in agreement completely what we measured in a nuclear spin polarized gas before. But what happens is that now they're going to have only 29% of the atoms in the interrogated atoms, and the others are going to be distributed in other nuclear levels. Or they can have, we can interrogate instead this transition, and then they have other distribution in the other levels. Or I'm going to interrogate this transition, but I'm going to have all the other levels. And the important part is that the slope of the density shift is going to be independent of the transition that I interrogate, because we have a SUN system. And the only effect of the spectator atoms is just to change a global offset. So for example, I have here no spectator atoms, so I don't have any offset. Then I have here only 29% of the interrogated atoms, and the rest are spectator atoms. So I see a global switch change it's just a constant shift independent of the excitation fraction. But all the time, no matter what, I will see the same slope independent of the atoms that I interrogate. And this is the fact that the slope is independent of what nuclear spin I interrogate. It's where we confirmed the SUN symmetry up to 3% level. I mean, we see that the slope is independent of any of these how the nuclear spin that I interrogate, and therefore the interaction parameters are completely independent of that. And with that, and using the slope and different measurements, we were able, with the help of Paul Julien also, that give us some relationship between the P wave and S wave interaction, to complete and determine all the possible scattering lengths that rules the physics of SUN strontium atoms. So we were able to compute all the 8 scattering parameters by matching the slope and by matching this alpha parameter that depends on the spectator atoms. We were able to determine all the different coefficients, including some lossy collisions that we have in the excited state atoms. So, and this opened us the possibility now to start exploring SUN physics, now that we have all the different scattering lengths at hand. And unfortunately, I want to tell you that when we were doing this experiment, actually, it was the person that was writing the episodes of Big Bang Theory, and he was a friend of June. So, they wanted to make a chapter of SUN magnetism in June's lab. And this was very funny. And then this chapter of the Big Bang Theory never appeared. But it was very interesting how we were contacted by the person, and June was, Sheldon was going to visit June's lab, and he was going to speculate about the SUN symmetry of collisions. But and then it never happened. Yes, but just wanted to, I will not have time this lecture, but I want to tell you that there is a full of things that are still happening in the clock. So all the physics that I told you about was a thermal sample. Now June has a three-dimensional quantum degenerate gas in an optical lattice, where we are able to explore SUN magnetism in the hover model. We are able to explore, there are a lot of physics. Unfortunately, I didn't have time to to tell you more. I mean, maybe on Friday, if we discuss, we have been able to measure multi-body interactions in the clock. So he was able to put more than 2 atoms per lattice site. He was able to put particles with 3, 4, 5, up to 6 atoms per lattice sites. And we were able to validate our characterization of the scattering parameters. And it was very exciting that he was able to measure even correction from multi-body interactions. If you are interested, I can tell you a little bit more on Friday. We have been able to measure now not only in the lattice, but in a trap. We were able to measure the thermodynamics of SUN gases and actually show that SUN interactions can significantly increase the magnitude of the interactions and can give a hydrodynamic behavior similar to what you can see in strongly interacting gases, but in a regime where mean field theory is valid. So we were able to characterize the expansion dynamics of the gas in the presence of SUN interactions, write a Boltzmann equation, and reproduce all the dynamics in very simple terms, where the SUN physics is cool because what it mentioned is that makes the scattering length n times larger than what you have with just SU2 gas. So we can see the anisotropic expansion of the cloud, and we were able to play with all of this. And of course, this physics is just starting. I mean, we have predicted that SUN physics can give rise to actually chiral spin liquids. It's going to allow us to do approximations that are not trivial, and because we can use 1/n and expansion parameters. We have Victor Gurari and Mike Emmerle here has predicted that in principle you can generate a SUN level n quantum computer. So it is going to be more powerful than any fractional Pfaffian state that you can prepare with in the fractional Hall effect, because this doesn't satisfy the criteria for universal gates. Seems that with SUN physics we should be able to do that. And there is a zoo of new states of matter that we should be able to observe. I mean, we have predicted, sorry, let me go here. In principle, we can predict chiral spin liquids, valence bond solids. We should be able to explore Hermite fermions with Kondo systems. We should be able to explore the physics of transition metal oxides. I mean, the physics is really ripe. And if you are in, I mean, hopefully, with this lecture, I could just tell you the beginning of what is happening and excite you about continue looking and investigating on SUN magnetism. Kaden is most likely going to give some lecture next week, and no, you will not tell anything about SUN.
I wasn't planning on it. We could take a vote, but we'll see.
Okay, yeah. So there is a lot of exciting physics ahead, and with that, thank you for your attention.
Thank you, Ana Maria. Maybe we just need 3 more lectures from Ana Maria to hear about these directions. Yeah, questions? So can you comment on, a lot of the work you focused on today was in this no mode changing collisions, and then you sort of went into this hydrodynamic description. Are these, how similar or how different are these 2 limits?
Yes, so actually we find that the mode changing collisions that are necessary to include by a collisional integral were only important in certain parameter regimes. So if you are very cold, the quantum degeneracy actually prevents this collisional integral. The collisional integral is a function of temperature. So if you are T/Tf very cold, the collisional integral is not very important. On the other hand, if you go to very hot gases, the system is so dilute that also the collisional integral is not important. It's just in the intermediate regime that when you have T/Tf of the order of between 0.3 and 0, I mean, maybe I can point this plot. So only in the intermediate regime here. In the intermediate regime between 0. I mean, for these parameters between 0.1 to 0.5, the collisional integral was important. But if you go hotter, they play no role, and if you go colder, they play no role. So it's just in a sweet spot where they are relevant. And it's just a tiny correction. I mean, the overall physics is not that different, but they introduce some corrections.
This SUN physics that you're talking about, I guess this is for the alkaline earth atoms, I guess you mentioned. Can this also happen in an analogous in alkali atoms, or?
They could happen if you go to a very strong magnetic field. I mean, here, remember the SUN physics is the decoupling between the nuclear, I mean, we have the electronic angular momentum and the nuclear spin, yes? So in principle, the problem in alkaline atoms is that at the typical magnetic fields that we work, we have to work not with I, not with J, but with the sum of both. But if you are able to work in a very large magnetic field, where the J and the I decouple, then in principle, you should be able to start to see a little bit of some of this SUN physics. And I think Ken O'Hara was trying to reach this regime with lithium atoms. I don't know where it go. I mean, he didn't continue to merge these experiments, but in principle, if you have a large enough magnetic field, it should be possible. Exactly. So Walter Hofstadter, he was trying to go to this regime exactly to look at SUN physics. I mean, one of his interests was attractive interactions. Unfortunately, so far in the alkaline atoms, all the scattering lengths that are S-wave, I mean, for the nuclear spin states are positives. So in principle, we will not be able to reach this superconducting limit that he's speculating to be possible in alkaline atoms. Maybe there are other atoms that have attractive interactions and might allow for the observation of this physics. Yeah.
Thank you.
So Anna Maria, so with the scaling ansatz that you're talking about for the Boltzmann equation, so this is a 2D gas that you're working with, or
3D.
So this is 3D. So the scaling ansatz, I guess, is pretty well justified in 2D because of the dilation symmetry. How accurate is this ansatz?
Very good if you have an harmonic oscillator dynamics. I mean, this is the expansion dynamics that we were talking about. So if it was, I mean, this is just you have a trap, release atom from the trap, and let the gas expand. And I mean, it's quite accurate. I mean, we were able, I mean, we were just solving this ansatz very trivially, and the agreement.
How did you determine that it's accurate? Just by comparing with the experiment?
With the experiment. This is the theory, and this is the experiment, and light's completely on top. And you can see this is the theory for SU10, and this is the experiment. So seems that it's working. I mean, the system is not very strongly interacting. That's the advantage. It's a mean field theory. I mean, it's not mean field theory. It's a Boltzmann equation, but it's not very complex theory.
But the scaling ansatz is a big approximation on top of the Boltzmann equation, right?
Yeah, but I think gases. I mean, if you have an harmonic oscillator, I mean, I think it has been checked even in systems in a strong Feshbach resonance. The scaling ansatz, I think, is very well justified because it's how it's a properties of the harmonic oscillator potential that you have some symmetries that they're not broken. Yes, I mean, even if you have non-interacting particles, you see that the harmonic oscillator levels are going to evolve in certain way that has this symmetry in the trap. So I think it's my understanding is that it has been very well validated for a trap. When you go in a lattice, it completely breaks down for sure. Yes.
I mean, so we had written a paper, I don't know, a couple of years ago about this using the scaling ansatz for SU in collective modes, right? And comparing with the experiments that Gyubung had done, Gyubung Zhou, and so there were always some discrepancies there, and we never knew, is it an experimental systematic? Is it a breakdown of Boltzmann, or is it a breakdown of the scaling ansatz? And so that's why I'm asking, because I'm curious these three possibilities it might be.
I see. Well, we saw very good agreement with the comparison with Jun's experiment. So I don't know. Maybe Maybe,
It was also, so 2D, so, you know, it could be a 2D, 3D thing, but I naively would have expected the scaling ansatz to work better in 2D than 3D, so yeah. Anyways,
yeah.
cool. Other questions? All right. So thanks, Ana Maria, for the great, this was your final lecture, I guess, so thank you
This
for
is my
all.
final lecture that will be on the Friday discussion. Mhm.
Yep. So talk to you Friday. Bring the rest of your questions Friday, and I will see everyone in the morning.
Okay, thank you. Bye-bye. Bye-bye.